Hello everyone, welcome to the Technogate. So today I'm going to start or discuss with the asymptotic notation. It's a very important topic of the algorithm here. So it is covering 2 to 3 marks every year. Okay, so there are three type of notations here. So first one is a big O notation, or we can say maximum time, or we can say worst case time. Okay, big O notation, maximum time or worst case, and denoted by the big O. Big O. Okay. Second one is the omega notation, or minimum time or best case. Okay. So best case is denoted by omega, like omega of n. This one. The big O and omega. Third one is theta notation, or average time or average case, and denoted by the theta of n here. So there are three notations here. Big O means worst case time complexity or maximum time. Omega notation or minimum time or best case time complexity, omega n. And theta notation, average time or average case, is theta of n here. Okay. So we will discuss one by one all the three notations, how to approach that problem, which type of problem asked in the examination. Okay. So let's check one by one. So first of all, big O notation. So here, let Fn and Gn be two positive functions then big O notation is what? Fn is big O of Gn. Let Fn and Gn be two positive function, then big O notation or big O notation is Fn is big O of Gn. So if Fn is big O of Gn, then Gn must be upper bound. Then Gn must be upper bound on Fn. Means function growth of Gn must be larger than Fn here. Okay, so big O notation. So Fn is big O of Gn if and only if if and only if Fn less than equals to C dot Gn here. This one is a big O notation. Fn is less than equals to C dot G of n. So C is a constant here. So C must be greater than 0 here. Okay, and n must be greater than equals to n0 here. Okay, so if this condition is satisfied, then we can say Gn growth is larger than Fn, or Gn is a upper bound is this one. So Gn is a worst case time complexity use. Okay, so Fn less than equals to C dot Gn here. So this is a big O notation here. So suppose that, take an example here. Suppose I am taking like that. Fn is n and Gn is n square here. So we can say Fn is big O of Gn. If Fn is big O of Gn, that means function rate or function growth rate of Gn must be larger than n here. So here n square here, this is n square and this is the n here. So we know n square growth rate is much larger than n here. Why? Suppose that this is n and this is the n square here. So if n is 1 here, then it is 1, it is 1. If n is 2 here, is it 2, it is a 4. N is 3 here, it is 3 here, it is 9 here. N is 4 here, it is 4 here, 16 here. So n square growth rate is much larger than n here. So here Gn, n square is upper bound on n square growth rate is much larger than n here. So here Fn is big of Gn. Okay, so what is the purpose of C here? See, purpose of C is only balance the equation. C is a constant here. Only purpose of C is balance the equation. So you write like n less than equals to C dot n square here. Suppose that we are taking C is one constant. So n less than equals to n square, yes. On 1, both are meet here. So n0 is what? Meeting point. So where two functions are meeting here, n0 is the meeting point here. So here n is less than equals to n square every time. After this point, there is no point where n and n square both are meet. No, this one. So, okay. Let's take another example here. So, like Fn is n square plus n and Gn is n square here. So we can say like Fn is bigger of Gn. How? So n square n. So what is the condition here? Condition is what? If Fn is bigger of Gn, that means what is this? Fn is less than equals to C dot Gn. C dot Gn here. So n square plus n less than equals to C dot n square. So what is the purpose of constant here? Balance the equation here. So here C is what here? Suppose C is taking 100 like that. C must be greater than 0 here. So 100 dot n square is greater than n square plus. So we balance the equation. So for any value of n, this one is multiplied with 100 and this one will be small other than this one. Yes or no? Yeah, this one. So this condition satisfy here. Fn is less than equals to C dot Gn. So we can write this. And second point is what is the shortcut here? Fn less than equals to here equals to there. So in both of the function, if bigger term or larger term are same, then we can write this one also, and we can write like Gn is big of Fn also. Why? Because through C we can balance it. Okay. So if both the terms here, higher term is n square here, higher term is n square here. So if higher term in both of the function are same, then we can write this one and this one both are same here. Because through C we can balance it. Clear? So this is a big O notation. Big O notation means maximum time complexity or worst case time complexity. Okay. Let's take one more example here. So we are taking like a Fn is n square plus n plus 10 here and Gn is n square plus n here. So again, both of the term in the function are n square here. So here Fn is less than equal to C dot Gn. So we can write like n square plus n plus 10 less than equals to C dot n square plus n. So through C we can balance it. Here. So we can write this one. So here Fn is big of Gn. So purpose of C is balance the equation only. Okay. So we will see how C works over or how C helps the function to balance the equation. Okay. So this one we can write this. Okay. Now next one is omega notation. Second one is the omega notation or lower bound or minimum time or best case. Okay, omega notation or lower bound or minimum time or best case. Okay, so let Fn and Gn be two positive functions, then Fn is omega of Gn, means this must be lower bound, so Fn is omega of Gn if and only if Fn greater than equals to C dot Gn. Fn greater than equals to C dot Gn here. So C greater than 0 here and n greater than equals to n naught here. Okay. So Fn greater than equals to C dot Gn, then we can say Gn is a lower bound on Fn. Means Gn function rate growth is smaller than Fn. Sometimes they meet after 1 point or 2 point, Gn growth rate is smaller than Fn. Okay. Suppose that we are taking like example here. Fn is n square here and Gn is n here. So we can say like a Fn is omega of Gn. So omega means this function must be lower bound. Okay. So and Gn is what? N here and this is n square. So n function growth rate, linear function rate is smaller than n square here. So yes, we can write this one. Okay. Or we can write this Fn is big of Gn. We can write this one. No. Why? Because big O means this must be upper bound on Fn. So here n here n square here. So tell me one thing. Function rate of n is greater than n square. No. So we cannot write this one. This is not possible, but this is possible. If this one is possible, if and only if Fn is n and Gn is n square. So Gn, so Fn is big O of Gn. We can write this one. So big O means upper bound, Gn must be upper bound here, and omega means Gn must be lower bound. Means lower bound means after some point Gn growth rate must be smaller than Fn, and here in big O, Gn growth rate must be larger than Fn. Okay, so this is the big O notation. This is the big O notation here. Next one is a theta notation. So there are two notation are over, big O notation and omega notation here. Next is a theta notation, means average time. So third one is the theta notation or average time, or denoted by the theta here, like this one. So theta is in between upper bound and lower bound. Theta is in between upper bound and lower bound here. So Fn and Gn, two positive functions, then Fn is a theta of Gn. Fn is theta of Gn. So this is the average time, means this one is between upper bound and lower bound here. So if and only if, first one is what? Fn is big of Gn, means Fn less than equals to C dot Gn, and second is Fn is omega of Gn. That means Fn is greater than equals to C dot Gn. Okay, so in between. So if these two conditions are satisfied, then Fn is theta of Gn. Means this is the average bound. So Gn is the average bound. This is the average bound. Okay, so this is upper bound and this is lower bound. So in between, if and all these two conditions are satisfied. So what is the common condition here? Common condition here is Fn equals to Gn here. So sometimes theta is called exact bound also. Why? Because left hand side and right hand side both must be equal here. So what is the common conditions from this here? Fn is equals to Gn here. Means left hand side and right hand side must be equal, then we can say it's an average bound. Then we can use the theta notation here. Okay, so these are the three notations here. Big O means maximum time or worst case time complexity. Omega of n is a minimum time or best case time complexity. Theta of n is a average time or average case time complexity. These three notations we are using. Okay, this one. Next, the graph, asymptotic graph here. How to represent through the graph with these three notations here. So first we will take big O notation. So suppose that this is the Fn or Fn and Gn here, function growth here, and here n will increase here. Okay, so suppose that is the meeting point. This is a meeting point here, like this is n0 here, and this is 0 here. So after this point, if big O notation is there, then Fn is big O of Gn. What is the meaning? Means Gn growth rate must be larger than Fn here. So Fn less than equals to C dot Gn here. Okay. So here C dot Gn, and this is the Fn here. Okay, this is the Fn here. So after some point of time, there may be chances they will meet. Okay, but after this point, Gn growth rate must be larger than Fn here. Suppose that like 2 raised to power n and n square here. So n is 1 here, this is 2, this is 1. Okay, n is 2 here, so this is 2, 4 here, yes, 4 here. So at 4 both are meeting. So n0 is what? 4 here, this one. After this one, so n is 3 here, 8, and this is our 9. Okay, n is 4 here, is it 16? It is 16. Again, this is the meeting point. Okay, but after this point, n is 5 here, this is 32, and this is 25. N is 6 here, is 64, and is 36. So after this point, there is no point where exponential 2 raised to power n or n square function will meet. Never chances here. Okay, so these are the meeting points here. So after this function, so last meeting point is what? 4 here. So in the examination they can ask like what is the last meeting point of these two functions? Is 4 here. So n0 is what? Meeting point here. Okay, so this is a graph, asymptotic graph for the big O notation, this one. Okay, so after this point, Gn growth rate must be, so Gn line will be higher than always Fn. Clear? Next one is omega notation. Omega notation or minimum time. So there are two functions here. So here Fn and Gn, here n here, this is n0. So this is Fn and here C dot Gn here. Okay, so after this point, Fn growth rate is larger than Gn. Gn must be lower bound, always lower to Fn here. So suppose that Fn is omega of Gn if and only if Fn greater than equals to C dot Gn here. C dot Gn here. Okay. So here Fn growth rate is always then Gn here. So Gn must be lower bound on Fn, omega notation, best case time complexity. So there are some points they will meet, okay, like n and n square. So here n is 1 here, 1 and 1. N is 2 here, this is 2, this is 4. N is 3 here, this is 3, here 9. So what is the meeting point here? 1 here. So at 1 both are meeting. After that n square growth rate is larger than n here. So this is the Fn and this is the Gn. So Gn is lower bound than Fn. Gn is lower bound than Fn. So this is a omega notation here. This is a omega notation here. Last one is the theta notation. So theta notation is in between upper bound and lower bound. Theta notation is in between upper bound and lower bound here. So let's check. So here, this is the meeting point here. So here Fn. So this is the Fn here. This is the C1 dot Gn upper bound and the C2 dot Gn lower bound. So Fn always exists in between upper bound and lower bound. Okay, so Fn is theta of Gn if and only if Fn equals to Gn. Means both of the side must be equal. Left hand side part and right hand side part must be equal. Okay, both must be equal here. Otherwise they will not work here. So these are three notations here. Big O notation. Big O means if Fn is big O of Gn, that means Gn must be upper bound on Fn. Okay, or we can say maximum time, worst case time complexity. Then we use the notation of big O notation. Okay, and second one is the omega notation, means lower bound means best case, means minimum time complexity. So if suppose that we are saying Fn is omega of Gn, means Gn must be lower bound than Fn. And third one is theta notation, average case average time. If Fn is theta of Gn, means left hand side and right hand side part must be equal. Okay, these three notations here. Okay, let's see what are the difference between big O notation and omega small O notation. There are two notations here, big O and small notation. What are the difference between these two? Okay, and one more is big omega and small omega also here. Let's see this one. What are the difference between this? Okay, so conclusion is what? So here, if n square is big of n square, okay, and n square is big of n cube, big of n cube. So here, this is a, we can say this is a tightest upper bound. Then we can say it is a tightest upper bound. Is a tightest upper bound. It is a tightest upper bound. If left hand side part and right hand side part both are equal, means tightest upper bound. But here left hand side is n square here and right hand side is n cube here. Both are not equal, then it is not the tightest upper bound. It is not the tightest upper bound. So tightest upper bound only we can say when left hand side and right hand side both are equal. Okay. So through bigger notation we can say a function is tightest upper bound or not. Okay. This one. Clear? So using bigger notation, we can find the tightest upper bound. We can find the tightest upper bound. We can find the tightest upper bound. Okay. But okay, we can find the tightest upper bound. We can find only the upper bound. Sorry, we can find the upper bound, but those upper bound may be tightest or may not be tightest. Okay. So here we can find means big O means is upper bound. So n square is upper bound on n square. Okay. N cube is the upper bound on n square. Yes. So using big O notation we can find the upper bound, but those upper bound may be tightest or may not be tightest. Okay. This is the tightest. This is not a tightest. So is the upper bound is the tightest or not tightest? We are using the small O notation. Small O notation. Okay. So next is a small O notation. So this one, let's see this. So small notation is small O notation. So in small O notation, Fn is less than C dot Gn. Okay, if Fn is small O of Gn, then what is the meaning? Fn less than only, not here. So equal to part is not included here. In less than equals to part, equal to part, not included here. So only what is the condition? Fn less than C dot Gn. Okay, so here suppose that n square is less than big O of n cube. Yes, n square is small O n square, n is small of O n. So here it is valid only because n square less than n cube. Yes, but it is not valid here because equal to condition is not exist here. Equal to condition is not exist here. Okay, so this one here. So which one is upper bound or which one is not upper bound here? So here using small notation we can find the tightest upper bound. We can find the tightest upper bound here. So it is valid here, it is valid here, it is valid here. Okay, this one is a small O notation here. Is a small O notation here. So using this notation, we can find not tightest upper bound. Not tightest upper bound. Not tightest upper bound here. Okay. So next one is omega notation. Let's see omega notation here. Small omega. So here Fn is small of Gn if and only if Fn greater than C dot Gn. Here again equal to part is not exist here. Equal to part is not exist here. So suppose here n square is omega of n square n square is omega of n square is omega of constant here. Okay, so this one is what here? This is a tightest lower bound. Okay, so this is the tightest lower bound, because left hand side and right hand both are equal here, and this one is a not a tightest upper bound, not a tightest lower bound here. This one also not tightest upper bound. So through big O notation, okay, through big omega notation, we can find only lower bound. Okay, so using big omega notation, okay, this is the big omega notation, like this is a big omega notation. Okay, this is a big omega. Using big omega notation, we can find lower bound. We can find lower bound only. Okay, but those lower bound may be tightest lower bound or may not be tightest lower bound. Okay, but those lower bound may be tightest or may not be tightest. Okay, so through big omega notation, we only find the lower bound only, but those lower bound may be tightest or may not be tightest. So maybe tightest lower bound or may not, we use the small omega notation. We use the small omega notation here. So in a small omega notation, n square is omega of n. Yes, it is valid. N square is omega of n square, not valid. It's small omega. Okay, this one is valid. Clear? So here we can find this through omega notation, small omega notation, we can find that lower bound may be tightest or may not be tightest here. Okay. So this is a tightest lower bound here. This is not a tightest lower bound here. Okay. This is a small omega, because here Fn greater than C dot Gn. Clear? So this is all about a bigger notation, big omega notation, theta notation, and all things are here. Okay, in the next upcoming class we will discuss the more of the gate problems. So how to approach the problem, how to pick the correct options, which one is a big omega notation, which one is a big O notation, theta notation, and all things, and how to approach. Okay, various different methods here. Okay, thank you everyone.